We talked back in section 7.5 about how not every integral can be computed exactly. So there's not rules for everything. There are some functions that just can't be integrated. For those, we need approximate integration. There's a couple of situations like that. E to the x squared, square root of 1 plus x cubed. Other situations are where we collect real-time data and we need to find the area under those curves. So we need approximate integration. And you learned some of these methods back in Calc 1. You learned about Riemann sums. You learned left endpoints, right endpoints, and midpoints. And you learned to do those on your TI-36X Pro calculator. Hopefully you went through and did your intro sheet with the graph with the velocities of a car traveling on a straight road for 50 seconds. So we want to, you computed the right and left and midpoint Riemann sums for these first 50 seconds using delta x equals 10, hopefully. Here's a little review of how to do left, right, endpoints, and midpoints. There may be some midpoint problems on your WebAssign. You won't be tested on it. You're going to be tested on the trapezoidal rule and Simpson's rule. So let's start by looking at this example that we did, and we'll introduce the trapezoid rule. It's kind of like the best of left and right endpoints because you just connect to the endpoints. So I did print out, and I went ahead and divided this into 5 sections. So these are my intervals. Delta x is equal to 10 because that's the distance between the two endpoints. And then I'm going to connect these 2 points. So the left endpoint and the right endpoint of my subintervals. And yeah, I'm not a great drawer, so I have to use my ruler a lot. Now, just like Riemann sums, it's just going to be approximation. It's not going to be perfect because we've got some extra stuff here. We got a good bit of extra stuff here. We lose a little bit of stuff there. But each of these has a width of delta x, which is 10. We need to remember what the area of a trapezoid is. Well, the area of a trapezoid is 1/2 of base number 1 plus base number 2 times the height. Well, in this case, the height of these trapezoids is your delta x. And your bases are going to be this endpoint and this endpoint, left endpoint, right endpoint, left endpoint, right endpoint. So let's just write that as left end plus right end. And I'll put quotes around them so it doesn't look like Lind and Rend. Left end plus right end. Now, let's think about what happens when we look at these. So I'm going to write them down. The area under this curve would be equal to 1/2. My left endpoint here is 0, and I'm talking about the height of it because 10 is going to be my width. So 1/2 of 0 plus 20 times my delta x, which is 10, plus 1/2 of, now my left endpoint, my right endpoint becomes my left endpoint, 20 plus 55 times 10 plus 1/2 of 55 plus 78 times 10 plus 1/2 of 78 plus 75 times 10 plus 1/2 of 75 plus 72. Oops. 72 times 10. Now, let's do some manipulating. Each term here has a 10, so let's factor 10 out. Each term has a 1/2, so we could even factor 1/2 out. I would have 10 over 2. Actually, don't do that. I don't want to factor the 1/2 out. I just want to factor the 10 out. Let's leave the 1/2s. So area is equal to 10. I have 1/2 of 0 plus 20 plus 1/2 of 20 plus 55 plus 1/2 of 55 plus 78 plus 1/2 of 78 plus 75 plus 1/2 of 75 plus 72. Now, think about distributing the 1/2s through the parentheses. So 10 is sitting outside. I have 1/2 times 0 plus 1/2 of 20 plus 1/2 of 20. I have 1/2 of 55 plus 1/2 of 55. I have 1/2 of 78 plus 1/2 of 78. I have 1/2 of 75 plus 1/2 of 75. I got ahead of myself. And then finally, 1/2 of 72. So, everybody except the endpoints gets a whole number because you have a half and a half and a half and a half and you add them all together. So what you really end up with is 10 times 1/2 of 0 plus the inside ones. So we would have 20 plus 55 plus 78 plus 75 plus half of 72. And here's the area under the curve, and that's exactly the same thing that I wrote right there. That is the trapezoid rule. So here's the area of a trapezoid. There's the pretty picture. And here is the easiest way to calculate it. You notice we have a 10 and we have a 1/2 here. So I really do want to factor that 1/2 out so I can have delta x over 2. If I factor a 1/2 out, I'm going to have to make up for it by multiplying by 2. So what I have is 10 over 2 times 0 plus 2 20s plus 2 55s plus 2 78s plus 2 75s plus a 72. That way I can factor that 1/2 out like I wanted to do earlier. And this is the pattern that you should memorize. Half delta x over 2 and then the first term, double all the other terms until you get to the last one. It just gets 1. Okay, so let's do example 1. We'll use the trapezoid rule to approximate this integral, even though we know how to do this integral. This is one we could calculate. So we're going to go from 1 to 2 dx over x. So find your delta x just like you did when you were doing Riemann sums. We want 5 rectangles. So delta x is equal to b minus a over 5. So 1/5. So my f of x is 1 over x. So my area is going to be delta x 1/5 over 2. And then I have to think about my endpoints. I start at 1, so f of 1, 2 times f of 1 and 1/5. So let's go ahead and use decimals. 1/5 would be 1.2 plus 2 times 1.4 plus 2 times 1.6 plus 2 times 1.8 f of, let me fix that. That will bother me if I don't. Don't forget it's f of 2 times f of 1.4, 2 times f of 1.6, 2 times f of 1.8, and then just f of 2. Now we'll use our calculator to do the heavy lifting. So this is 1/5 over 2. You could just write it as 0.1 or as 1/10, either way. Now, clear out the old stuff. F of 1 would be 1 over 1, which is 1. 2 times 1 over 1.2, which gives me 5 over 6. That's 2 times 1 over 1.4, which gives me 5 over 7. Plus 2 times 1 over 1.6. So this is going to be 5 over 8. Let's see. Clear that out. 1 over 1.8. It's 5 over 9. 2, 1.4, 1.6. Did I do 1.8 instead of 1.6? I did. I plugged in 1.8 instead of 1.6. I don't want to leave 1.6 out. Plus 2 over 5/9 plus, and then just 1/2. So 0.1. I'll do some multiplying. 1 plus, we could cancel that and have 5 over 3, 10 over 7, 5 over 4, 10 over 9, and 1/2. Now, you could use your calculator and use your, clear the old stuff and use your table. So you could go in, edit your function, clear out that old function, and put 1 over x. Quit. And then we could type this in directly. So I could type in f of 1, so table, enter 1. That gives me 1. F of 2, table, enter 2, 1/2. Table, enter 1.2. I should have gone to that table. Enter 1.2 is 0.8333, which is the same as 5 over 6. So you could type it in directly if you wanted to. You could do table, enter f of 1 plus 2 times f of 1.2, close that set of parentheses, plus 2 times f of 1.4, close that set of parentheses, plus 2 times f of 1.6, close that set of parentheses. You can see it's easy to get lost and make a mistake, plus 2 times f of 1.8 plus f of 2. And then it will do all of that adding for you. We get 6.96. Now let's see how good an estimate we have. We can look at the second integral from 1 to 2, and since I already have my function in there, I can just do f of x. I'll just do 1 over x. 1 over x. And it's about 0.69, and that's because I needed to multiply that by 0.1. This final answer is actually 0.1 times 6.96. 6.956, which is 0.696. Let's look at my pretty answer. There we go. So you can see it's kind of cumbersome going through all of that with your calculator. So let's use a tool that you can use to do your web assigns, but not on test day. We'll go ahead and try one of these with Excel. So this is example 1, the exact same thing that we just did. Let me make this bigger so we can see it better. There we go. And I'm going to make a little table. When I'm using Excel, I like to make a table. You can make a table on your paper if you want to. I'm going to make a column for x, a column for f of x, a column for what I call my multiplier, and then a column for the product of those two things. So my first x is 1. My next one is 1.2. These are the inputs, 1.4. And of course, once I establish a pattern, Excel will continue the pattern until I tell it to stop. F of x is equal to 1 over x. And it calculates all of those for me. My multipliers are 1, 2, 2, 2, 2, 1, because that's what I multiply each of those terms by. And then this is the product equals f of x times the multiplier. Then I asked Excel very nicely to add those up by putting my cursor below the list of numbers and hitting auto sum, or you can type in equals sum and select what you want. And then you need to multiply by delta x over 2. And delta x over 2, let's don't do that right there. Let's put it over here. Delta x was equal to, open up parentheses, 2 minus 1 divided by 5. And then delta x over 2 is equal to this thing divided by 2. So we want to multiply, so let's say times delta x over 2 over 2, not 1. And let's make that row column bigger. So equals this times that. And that gives me the same answer. So you can use Excel for your WebAssigns. You can't use Excel for your test day. So I won't give you a big long one. I wouldn't give you anything longer than this, say, on test day. Actually, that's a lie. I might give you 6 terms, but I won't give you 20 terms on test day. So let's go to Simpson's rule. Simpson's rule is even better. It uses little parabolas. Now, unfortunately, I can't show you exactly how the formula works because it's not as simple as trapezoids, who are 1/2 of base number 1 times base number 2 plus base number 2 times the height. But we do the same divisions and we draw little parabolas. And you're just going to have to memorize it. It's delta x over 3, so instead of 2, it's over 3. And our pattern is different. The first and the last still get 1s, but instead of everybody else getting 2s, it's 4, 2, 4, 2, 4, 2, and you have to have a 4 right before the 1. So you have to have that pattern of coefficients. Let's look at the same example using Simpson's rule, and we're going to use 10 rectangles or intervals. Example 4. So we want to approximate the integral from 1 to 2, 1 over x. So my delta x is going to be equal to 2 minus 1 over 10, which is 1/10, or 0.1. And now let's just write down the formula for it. If nothing else on test day, if you think you're going to get lost in all these numbers, at least write down the formula and the pattern and you'll get most of the points. So area is equal to delta x over 3. Now this time my delta x is 0.1, so my first input is going to be f of 1, and my second will be 4 times f of 1.1, 2 times f of 1.2, 4 times f of 1.3, 2 times f of 1.4, 4 times f of 1.5, 2 times f of 1.6, I will not ask you to do 10 terms on test day. 4 times f of 1.7, 2 times f of 1.8, 4 times f of 1.9, and then plus f of 2. You notice we start and end with 1, 4, 4, 1. And then alternate 2s and 4s in between. I'm not going to plug this one into the calculator. Here's the pretty answer, and you get a little better approximation. Let's look at Excel. Here's Simpson's rule with 10 integrals. So we'll start with delta x is equal to 2 minus 1 divided by 10. There's my delta x. And again, let's make this not that big. That looks better. That way we'll be able to see what's going on. Now I'm going to make a column for x, just like I did before. A column for f of x, a column for my multiplier, and a column for the product. So my x starts at 1. I increment by delta x, which is 1.1. And you can keep typing if you want to, but I'm pretty lazy, so I'm just going to keep going until I get to 2. Equals 1 over x. Does all that arithmetic for me. I love Excel. You should really learn to use Excel. My multipliers are 1, 4, 2, 4, 2. Let's see if it'll continue the pattern for me. I think it will. I would highlight those 2. Nope, it doesn't. So we just have to type it in. 4, 2, 4, 2, 4, 1. So 1 on top, 1 on the bottom, 4, 2, 4, 2. You could have cut and pasted it. Equals f of x times, not minus, times the multiplier. Ask Excel very nicely to add it up for you. So this is equal to the sum of f of 1 plus 4 times f of 1.1 plus 2 times f of 1.2, etc., etc. We need to multiply this by delta x over 3. So delta x over 3 is equal to 0.1 divided by 3. So when we multiply those things together, we get our answer, which is this times delta x over 3, which gives me 0.69315. Alrighty. Now we're asked to do example 7. We want to do the trapezoid rule and Simpson's rule with n equals 10 to do something that we can't actually find the integral of. So let's look at this example. We'll write it down, and then again, I'm going to use Excel to do the heavy lifting for me. So we have the integral from 0 to 1 e to the x squared dx. Delta x is equal to 1 minus 0 divided by 10. 1/10 or 0.1. So the area under the curve is going to be equal to, and let's give it its appropriate name, the the trapezoid rule with 10 sections would be equal to 1/10 over 2, and I'm going to call this f of x again, and I would have f of 0 plus 2 times f of 0.1 plus 2 times f of 0.2 plus 2 times f of 0.9 plus f of 1. If you really wanted to, you could use your summation button and add up the middle ones and then add the 2 ends to it on your calculator. Be a little bit easier than doing everything by hand. Simpson's rule with 10 intervals. Same delta x, but now we're over 3. We still start with 1, but now we have 4 times 0.1, 2 times f of 0.2, 2 times f of 0.8, 4 times f of 0.9, plus f of 1. I'm going to use Excel to do the work for me. Did I close my Excel? I did close my Excel. I'll have to open it right back up. There we go. Example 7. Trapezoid rule and Simpson's rule. So I'm going to go ahead and make it bigger. We already know what our delta x is. I'm not going to rely on Excel to calculate that for me. We'll do x, we'll do f of x, we'll do a multiplier, and we'll do product. My x's go from 0 to 0.1, and let's go ahead and make this big so I can drag it easily until it gets to 1. Equals. Now, the Excel way of writing e to the x squared is exp, open up a set of parentheses, x, and then squared. So instead of e to the, you write exp parenthesis. And then either you get the solid plus sign and drag to the bottom, or you get the solid plus sign and double click. We'll start with trapezoid. That means our multipliers are going to be 1, 2, 2, 2. Our product is going to be equal to f of x times the multiplier we add it up. Let's go ahead and label this. So your sum, delta x over 2 would be equal to 0.1 divided by 2. And then my answer is this guy times that guy. Now, I'm going to be super efficient and copy these first 2 columns. So Control C, Control V. Multiplier, product. I could have copied the whole thing actually and then just adjusted the multipliers. So let's see. Let's be super lazy. but this needs to change to 4, 4, 4, 4, 4. Still need to add them up. So here's the sum, but I need delta x over 3, so that would be equal to 0.1 divided by 3. So my final answer would be equal to this guy times this guy. Oh wow, they're really close, but your Simpson's rule is going to be a little closer to the true answer. So that's how you do it when you're given a function. You have to plug the numbers in. Very often you're not going to be given numbers. It's not going to be a function that you can't integrate. It's going to be getting the area under a graph. So let's estimate the area under this curve using the trapezoid rule and using Simpson's rule. I decided to print myself out a big version of this one. So I want to do an estimate using trapezoidal rule with 6 intervals. So 1, 2, 3, 4, 5, 6. It's pretty obvious where they are. My delta x, you can either look at it as the difference between two successive inputs, or 6 minus 0 divided by 6 is 1. So my delta x is equal to 1. So we have 1/2 times my first output, which would be 2, then 2 times the output at 1, plus 2 times the output at 2, plus 2 times the output at 3, plus 2 times the output at 4, plus 2 times the output at 5, plus the output at 6. 1, 2, 3, 4. And then it's just some arithmetic, so I'll pause for a minute and do the arithmetic. Okay, I did do a little bit in my head. I did the multiplying, the 2 times 4, etc. And I did go back and fix that where I had accidentally written down 3 instead of the output at 3. So I do have the right answer here. I added them all up and then I multiplied by 1/2 instead of distributing. So I ended up with 19. And now with Simpson's, we have 1 over 3. Delta x is 1 over 3. Same outputs here. So we have 2. Then we have 4 times 1. We have 2 times 1, 2, 3. We have 4 times 1, 2, 3, 4, 5. We have 2 times 1, 2, 3, 4. We have 4 times 1, 2, 3. 1, 2, 3, 4. I'm going to do the arithmetic and we'll come back and compare answers. Plugged it into the calculator, added, and then I just divided it by 3. I ended up with 56 over 3. Hopefully that one went okay. Let's try another one. This one, we are trying to find the area of this kidney-shaped pool. The width in meters of this kidney-shaped swimming pool is measured at 2-meter intervals as indicated in the figure. Use the trapezoid rule and Simpson's rule to estimate the area of the pool. So we have to think about going from end to end. So the width at this end is 0, and the width at this end is 0. So I think I'll just use the back of this sheet of paper and do this one. That's the next example. I'll move that out of the way. This is practice number 2. And how many intervals are we using? Well, we're doing 1, 2, 3, 4, 5, 6, 7, 8, because that's how many little sections there are. So I'm going to call this T8. My delta x is the width of the interval, and it says they're 2-meter intervals. So delta x is equal to 2. So I have delta x over 2 times the first input is 0, 2 times 6.2 plus 2 times 7.2, 2 times 6.8, 2 times 5.6, 2 times 5, 2 times 4.8, 2 times 4.8, plus 0. And then, again, it is arithmetic time. I'll pause. Now this one, I just mentally factored the 2 out, and I just added up the numbers, and then I multiplied the result by 2, and I ended up with about 80.8 square meters. Let's do the same thing for Simpson with 8 intervals. This time we have 2 over 3. We're still going to start and end with zeros because we have 1 times 0 at both ends, but we have 4 times 6.2, 2 times 7.2, 4 times 6.8, 2 times 5.6, 4 times 5, 2 times 4.8, 4 times 4.8, and 0. I'll add those up. That one I did have to type in all the multiplying, but then I just did all this adding and then multiplied by 2/3 at the end, and I got about 84 square meters. So Simpson gave me a little bit larger area than Trapezoid gave me about 81 square meters for the area. Yep. I think just one more example. A graph of the temperature in Boston on August 11th, 2013 is shown. We want to use Simpson's rule with n equals 12 to estimate the average temperature on that day. And I did print that out for us just so I can see those estimates a little bit better, because that's a very small graph. So we want to use n equals 12. And since our input is going to be, let's see, we have the graph and their temperatures from midnight, so it's 24 hours. So we'll say that our input is hours since midnight. That means there are 24 of them in a day, so delta x is equal to 24 hours divided by 12 intervals. So every 2 hours we want to look at the temperature. So right here, 4, 6, 8, 10, noon, 2, 4, 6, 8, 10, midnight. So this would be 12. And we could say it's the integral from 0 to 24 hours of the temperature. And let's call that capital T. Since we have little t as our inputs, we'll have capital T as our outputs. So we would have delta x, which is 12. No, delta x is 2 over 3. Because for Simpson, it's always over 3. Our first input is at midnight, so that would be, I'm going to call it 64. If you called it 63 or 62, I would be okay with that. 4 times the temperature at 2 a.m., and I'm just going to call that 65. Actually, yes, since that's 65, this is 60, that should be 67. I didn't read my scale correctly. So this would be 65 plus 2 times, gosh, not much difference. We'll call that 64 plus 4 times, I'm going to call this, let's see, this is 62 plus 2 times, let's call this 67, 4 times, let's see, 72. You're going to get a different answer. Nobody's going to do this exactly the same. If you called that 68, that's okay. If you called it 3, that would be wrong. But as long as what you have is reasonable, it's okay. Then we have 2 times, let's see, this was 72, noon. Oh, good, that's right on a line. We'll call that 75. 4 times, this is 75, so we'll call that 77. 2 times 79. That is right on 75, so 4 times 75 plus 2 times 75 plus 4 times, this is 71 plus 68. Good enough. It's not exact, but that's okay. We don't have exact numbers here, and it's just going to be approximation anyway, so I'll take a minute, I'll add it up and see what I get. So, what I have here is the area under this curve. I just added and did my multiplying. But I need to carefully read what I'm asked to figure out. This is a graph of the temperature in Boston on August 11th. We want to estimate the average temperature. So my average temperature is going to be equal to 1 over the number of hours. So 1 over 24 minus 0 times the integral from 0 to 24 of my temperature function. So I need to take this number that I got here and divide it by 24, and I get about 70.6 degrees. And the answer in the textbook was 70.8 degrees. So me and the authors, we did our estimating slightly differently. So be sure that you read the problems carefully. There's one on your lab where you need to find an average, if I remember correctly. So be sure that you find what you're asked for. Or if not an average, you have to manipulate it in some way. So be sure you answer what you're asked for. The other one just wanted the area of the pool and the area under the curve, but this one asked you for an average. So you have to remember that average value from back in Calc 1. You can do this. You have the tools you need, and you won't be asked for anything on test day that you can't do.